Hi guys, welcome back. Today we're going to be taking the sequence that we did last time and we're going to be expanding on it and making it sound a bit more interesting by adding some cool modulation effects. We're going to start by taking another simple oscillator, feeding the one that we're currently controlling with the sequencer into it to come up with a cool modulation synchy effect, and then we're going to go on and do some other cool stuff. Stay tuned. So, I said we're going to start with a sync effect. What do I mean when I say sync? Well, a hard sync in an analog oscillator is when you take one oscillator, so let's take a triangle wave oscillator, looks like this, right? So one period, whatever. So this is one period from here to here, so right? Maybe I should have drawn that down there. And so this time period, right, from here to here, that's the frequency, right? If we divide this, but if we divide 1 by this, so any frequency, in case you didn't know, is 1 divided by the time period in seconds. So if this was happening over a period of 1 second, that'd be 1 hertz. 1 divided by 1 is 1. If this was happening over a period of 2 seconds, then that would be 1 over 2, half a hertz. If this was happening over half a second, it'd be 1 divided by a half, which would be 2. So basically, what a hard sync does is, at the end of this period, you take another oscillator that's, say, running alongside this. Let's just assume it has a different shape. It's some other periodic thing. But at the end of this, right, it just forces it, boom, to reset and start again. So you're using this oscillator to control the frequency of this oscillator so that you can control the pitch of this oscillator, but not the timbre. So you can control the pitch of this oscillator with a different oscillator, and it has a certain sound. We're not going to be doing that explicitly, but we're going to be doing something that kind of mimics the sound of that. And what we're going to do is, as I said before, we're going to take one oscillator and we're going to bang it straight into the input of another one. And we're going to be using a diode so we can have a little bit more of a investigation into what a diode is and how it works. So, let's start with, we'll draw one of our oscillators. Right, so we got, so again, this is our Schmitt trigger symbol, remember? This is triangle, means it's an op amp. This symbol means it's a Schmitt trigger. Right, that doesn't matter for now, but when we go on, quite soon we'll be using generic op amps, and then you'll see that there is a difference. Okay. So we've got a feedback resistor here. What was this? 100k. Yep. We got a potentiometer. We got a capacitor, sorry, not a potentiometer. Right, and that goes down to ground. And we know this. We've done this a million times by now. And so what we're going to do now is we're going to put a resistor here. And all this is going to do is that's just going to limit the current output of this to make sure that the next chip doesn't get overdriven. What will this be? Let's just say this is, I can't remember off the top of my head what it was on the board. Let's just say it's 1k. I think it's either 1k or 10k. It doesn't matter. You don't even strictly need that. You know, it won't break without it. It's just a good idea to have. And then we're going to have a diode facing back this way, right? So I'll explain that in a second. And then we've got just another thing, more or less exactly the same. We know this. We kind of know this. We looked at current limiting resistors a little bit. You don't even really need to understand current limiting resistors from a scientific point of view. You just know, bang a resistor in there and it will limit the current to a certain extent. If the thing blows up, your resistor wasn't big enough. It can be that simple sometimes. So the only really new thing, and it's not a new thing, but well, yeah, it is actually. We've not used a diode before. is this little diode. So what is this little dude? So diodes, this is the symbol for it. Another triangle with a line. Okay, that's the circuit symbol. This is the plus side, this is the minus side, or this is the anode, and this is the cathode. Right, I remember anode. It's got the little and symbol here. A bit of silly, but whatever. Hopefully that helps you remember which way around it is. So the cathode, when you see it in real life, it's a little rectangular shaped thing, and it will have a dark band here on the cathode side, and it has two legs. It looks kind of like a resistor, a really small, like this casing is usually clear. You can get lots of different types of diode. We'll go over semiconductor devices in a whole video just on semiconductor devices a bit down the road. I don't really want to get into theory, like all the heavy theory stuff, until we've got some interesting like practical stuff done, because I kind of feel like we will learn by doing, rather than me stand there and be like, oh, well, semiconductor is dope it with this, because you're just going to switch the video off because it's kind of boring. It's not boring, but it's not thrilling either. So I think the common description of what a diode is that it blocks this way, right? So it won't allow current to flow from the negative side to the positive side. That's not really true. That's not really how it works. And again, if you only knew that description of it, this configuration seems completely baffling, because you're like, well, how is this signal going to get from here to here if it's being blocked by this diode? That's not how this circuit works at all, but you'll be forgiven for thinking that. It's actually the blocking action of the diode that makes this circuit work, and we'll get onto that. So how a diode works is if this side is more positive than this side by some amount, about 0.7 volts for a silicon diode and about 0.3 volts for a germanium diode. You look on the data sheet for your type of diodes. The silicon diodes are much more common. If you know about transistors, you'll know the base emitter drop in a BJT is 0.7 volts, and that's because you can kind of think of it as a diode across that junction. This side needs to be more positive than this side by about this voltage or more for the diode to act like a short circuit. So if this isn't true, then it will look like in the circuit, if we just get rid of this diode, it will look like an open switch. So nothing can flow either way, right? If this is closed, i.e. if this side, so this was our plus side, because we had it facing from right to left. This is the minus side. So either this side must be more positive, well, this side must be more positive, but the way you would think of that is like, right, so this side needs to be 0, and this side needs to be 0.7, right? Well, yes, correct. That would work, and that would close this, and that would allow current to flow in either direction. Obviously, this is a kind of DC circuit, so how can current flow against the voltage? Like, you can't. Conventional current flows from high to low, so how could you have it going the other way? But if you've got AC circuits, it gets a bit more complicated than we're just talking about it in a simplified manner. So yes, this, as I've got it written here, will close the switch, will turn the diode on, and will allow current to flow this way or this way. But on top of that, you need to remember that the diode can also function if this is 0 and this goes negative, 0.7 or more, you know, if this was 0.1 or whatever, which can very easily happen by accident if you have capacitors discharging. Capacitors, I've not really got any room on here, but kind of do this when they charge and discharge. They go like this, and that'll be a charging cycle, and then when they discharge, they swing negative. And so that can very easily ruin your circuit if you don't know. So be careful of these, and just be aware. And you can't. The other thing about diodes is they will block coming this way, right? So if this is ground, say, you can apply almost any voltage to this, you know, 5, 10, 20, 50 volts. Eventually though, just like anything, they will eventually break down. They've got some voltage where eventually the voltage is high enough. Remember, voltage is a force. The force is high enough, there's enough potential energy here to just destroy the diode, basically. It's a little chemical thing going on in here. There are electrons moving around and widening a little. There's a depletion layer in here where there's no electrons, basically. So you can imagine there's a little kind of hole in the middle of here, and it acts like an insulator, but there will be a voltage where that doesn't matter. That gap isn't wide enough to stop the voltage kind of jumping over, like you can imagine it kind of arcing over. I'm trying to describe it without going too much into the physics of it, because it is a little bit complicated, and it doesn't matter. So, and that'll be on the data sheet, you know, it'll be rated at that. So you'll get a diode, and it'll be rated in terms of its forward voltage drop, which is the drop that you need to exceed to turn it on, and also in terms of its reverse voltage or its breakdown voltage, which is the maximum voltage that it can take going in the other direction. So that's a brief rundown on diodes. Let's get back into talking about how this circuit works. Okay, so if we cast our minds backwards or watch it again if you've forgotten, the very first video I did, which was about the operation of this circuit chunk here, you'll remember that what we've essentially got is we've got a pattern, a square wave pattern. So this axis is time going across here, and this is voltage. Right. And we've got a repeating pattern, assuming that I don't touch any of these, of a square wave going like this. Right, cool. And we would have a similar one or an identical one. Well, it would be faster because we've got a smaller capacitor here. If, let's imagine this diode wasn't there for a second, that would just be doing its thing. So, what's going to go on? What is going to happen when we connect these two circuits together? Well, so they both start off in a kind of off state at the inputs. So, these are inverting, remember? So this output is going to go high. This input is low. So we're going to have 9 volts here. Right, and let's just ignore the resistor for a second. And let's just say there's 9 volts here. So there's 0 volts here. I'm just going to erase this resistor, so that we don't get confused and hung up on the resistor, because the resistor is not an important part of the circuit as far as the operation is concerned. I just want to keep it simple, keep as few moving parts in there as possible. There will just be a voltage drop across that resistor proportional to the amount of current, which at the moment anyway is 0, because let me mark the anode and the cathode on here. This is the anode and this is the cathode. So you can see the cathode is more positive than the anode, so no current is going to flow. There is a tiny leakage current. It's usually in the order of like 10 to the minus 14 amps. So 0.13 noughts and a 1 amp. Let's forget about that. So what's going to happen? Nothing, right? Well, no, not nothing, because we know what's going on here. This started off. So again, this is inverting, so this is going to turn on. It's going to come over here. This is an open circuit, so it's going to charge this capacitor up, just like we did over here, and we're going to get a charge-discharge cycle. It's going to be faster than this one was, so this one's going to charge and discharge inside here. Right, sweet, cool. Whoops. Not my pen. Okay, nice. So does that go on forever? No, it doesn't, because there comes a point where this output goes low. This is charged up to the point where it registers at the input of here as logic high, and so this inverts and flips the output low. So now we need to think about what does it mean to have a low output. Before we were just kind of not thinking about it, but let's say this output goes to 0 volts. What does that mean? How can the output go to 0 volts? So you need to remember that there's a power supply here, right? So this is plus VDD, or whatever, let's just call this, to save confusion, plus 9 volts. And this is a ground, right? This is at 0 volts. And so when the output is high, the output here is sourcing current, right? It can deliver current to the rest of the circuit. And when it goes low, the output then becomes a current sink, and current can flow in to the chip. And that's exactly what's going to happen. So before, when we had this short-circuited, this this capacitor would discharge through this resistor and into the output of the chip and down to ground, because this is the low potential. This was at around 6.66 whatever volts, but that's not what's going to happen this time. Well, that is what's going to happen, but what else is going to happen is the same thing's going to happen over here, because where's my red pen? Down here. So this is charged up, so these are both charged up, but the output here has flipped to 0 volts. This is 0 volts. So this is at some voltage. Let's just say it's at 7 volts. My pen's running out. This is at 7 volts. So this is at essentially 0 volts. Right, it's going to be at 0 volts at first before any current starts to flow anyway. So now this side is more positive than this side, right? So this is now going to act like a short circuit. It's going to have 0.7 volts dropped across it. And so now what's going to happen is this is going to discharge through here. And this is also going to discharge through here, just like it would normally. But this is the unusual thing, or this is the new thing rather, it's not unusual. And so now, try as it might, this cannot charge this. This cannot charge this capacitor. Anything. So this output will go low after one cycle. Let me put that on there. I'm obviously massively exaggerating these periods so that it's a bit clearer. My drawings are bad enough as they are. And so this is going to try, this has gone low, this is going to try its hardest to charge this up. I mean, this doesn't know what it's doing, but the input here is low, so this output is high, and it's going go, go, go. But it can't, because it's tied to ground. This input here is grounded. So it's all just going to flow out here, it's going to flow out here, it's going to flow out here. And after a period of time, this capacitor is also draining down to ground through this resistor. But then that's going to discharge to a point where the whole thing, we get over to here, the whole thing starts over again. This sees that this is discharged to the point where it reads a logic low on the input. It inverts, flips the output high. This side of the diode is now higher than this discharge capacitor, remember? It's going to be higher, so it's going to block. It's going to allow this to start charging and discharging again. This cycle will continue. And so we can see we've got two correlated waveforms. Now this red waveform is at a much higher frequency, but the fact that it is kind of amplitude modulated, you can think of it as, or controlled or synced by this first oscillator, gives it a really unique sound that you heard in the little demo at the start of this video and at the start of the last video. I couldn't fit it onto the last video because it got on long enough. And this is how that works, and it's a super easy way to use another one of those things on your chip. And so you turn this, and so you want to set the capacitor of this so that the timings, it doesn't allow this charge-discharge cycle to become longer than this charge-discharge cycle, because you can kind of see if this gets longer than this blue one, the red one gets longer than the blue one, then the sync effect isn't going to work. You're not going to hear it because there's not time for this capacitor to charge up before it gets grounded again by this op amp. So there's your sync effect. Let's go have a look at it on the board and then we'll move on to the next thing. Okay, so here's a quick shot of the breadboard. It's not the best shot in the world, you can't really see that much that's going on, but I just wanted to show you very quickly, before we go on to a proper demonstration, the 3 oscillators that we've got going on here. You can tell where there's an oscillator because we've got these capacitors in here. Let me try and squidge some of these wires out of the way. Alright, so here's our first one. This is our clock oscillator. You can see this is the nice huge 10 microfarad capacitor, I think that is. And that's just controlling the clock for the sequencer. That's what we did last time. Here's our first of our 2 oscillators. This is the one that's actually controlling the main pitch. This is the one being controlled by the sequencer, and this is what we built last time. And finally there's a third one over here. And as I said, it's exactly the same as all the other oscillators, it's just got a smaller capacitance. So let's give it a listen. Right, okay, so here we are on the oscilloscope and we're looking at the 2 oscillators. Now let me just pause this. Ooh, nice. It's quite a good example. So here we can see the blue trace on the oscillator is our first oscillator, right? And this is the one controlling the pitch. So essentially we've got 2 oscillators running. This is our pitch oscillator, which is going to dictate our perceived pitch, and this is the kind of sync oscillator which is going to run alongside this oscillator and give us that sync effect. I'll let you see how that sounds. So this is the first oscillator, and then this is the output of the sync oscillator. So you can see, because I've got it set to a resistance that allows it to oscillate in between the pitch settings, you can't really hear that pitch because this is kind of overriding it with that high frequency tone. But if I change this oscillator, oops, that's the speed I'm changing. There we go. I just accidentally had it set too high. So we can see now that we can hear that. Let me switch back to the first oscillator. So this is the blue trace you're hearing now, and now this is going to be the yellow trace you can hear. And now if I change the resistance for the yellow trace, remember the blue trace, the resistance is being selected with that multiplexer that we built last time. So the perceived pitch never really changes, that, but it gives it that sync modulator. It kind of sounds like a ring mod or like FM kind of sound. And as you go up, you can hear the sync effect kind of starting to dominate the sound now. Like you can hear it more as its own distinct pitch. And now they're really, you can hear there's multiple pitches going on there. It's very much like a ring mod sound now. And then it just cuts out. Pretty cool, huh? Alright, thanks a lot. See you next time.